Good evening, everyone. How are we all? Hopefully the bandwidth's okay now. Let me know if it starts lagging at all. Oh, it's a good start. Yeah, I was looking at that Screwdrivers game. It actually looks really good. It's kind of like my dream Lego racing game. If only I had time to try it, which is very much not the case right now. Thanks, yeah, the birds are doing good. So, on Sunday's stream, we had to cut the stream short because we had a couple of pigeons in our tree, and they completely abandoned their chicks, never came back. I don't know what happened to them, but they haven't been back since. So we had a couple of literally day-old pigeon chicks in a nest, and they were covered in like fly eggs. So they'd suffered fly strike. So we took them in, cleaned them up, got rid of all the fly eggs, and we've been feeding them with a syringe, and so far so good. They seem to be growing, and they're warm, and they're healthy, and their crops are full. So looks like we've just inherited 2 pigeons. Not quite sure what we're going to do with them yet. I think we'll have to build a nesting area in the tree or something. Hey Wes, yeah, I was one of the former developers on Stage 9, and I was co-project lead on the Orville fan experience. So most of the old Stage 9 team moved over to the Orville, and since then, most of them are now working for the Roddenberry project. But I really wanted to make Star Sim. It's kind of where my heart lay, so I've had a burning desire to make this specific game for a very, very long time. So I sort of went my separate ways from the old team and made this game instead. We're still very much in contact though. Yeah, you can definitely see some of the heritage there. We actually share some QA guys. They do QA for both projects. Yeah. It was actually me that added the disco mode to the Orville. I didn't do the original disco mode though, on Stage 9. That was probably Rob that did that. Yeah, we approached Fuzzy Door Productions, let them know what we had done for Stage 9. We put together a slide pack kind of showing the number of downloads and how much interest we'd had. It had like 2 million impressions. It was well loved at the time. And they got back to us and said, yeah, we'd love for you to do the same thing for the Orville. Obviously the usual caveats, it has to be non-profit, you're not allowed to charge for it, but under those conditions we were allowed to proceed. In fact, one of the coolest things of our dev career is that Seth MacFarlane actually tweeted out the project twice, saying how much he loved it, so that was pretty cool. And Tom Costantino, the executive producer, said that my interiors were scarily accurate, and he was particularly impressed that I'd included all the fire detectors. But all of that was just practice for what I'm doing now. Speaking of which, what am I doing now? So, on Sunday's stream, we were going through and sort of refining the planet gen data and dealing with some weird display issues with some of the data structures. That should now all be fixed. And I've been further refining just how we go about generating a star system. So the original version of this was very much dice rolls, and I wanted to move away from dice rolls into something that was more in keeping with how real star systems form. So what I've done is I've started with every planet being a rocky body to begin with, and it will step by step define how far from the star the planet is, work out all the orbital characteristics like its major and minor axes and that sort of thing. Once we know how far away it is, we can calculate an equilibrium temperature. We can then run a core mass accretion simulation. So we're using the core mass accretion model for our star systems, whereby rocky bodies form first as the base of any planetary body. We then determine how much iron is within that rocky structure. Obviously, the further from the star you are, there's less iron. Knowing all of this, we can then work out the radius, which then gives us the volume, and then depending on the planet's overall mass, we decide whether or not it's a gas giant. Generally speaking, 10 Earth masses is enough to have runaway gas accretion, so that's what we're going with for this. So if the core rocky body is more than 10 masses, then we then simulate runaway gas accretion and it becomes a gas giant. If it's less than 10 Earth masses, then we treat it as like a super Earth or an Earth-like, depending on its mass. I was also defining dwarf planets as being less mass than Titan, because Titan's kind of on the borderline as to how small a body can be and hold on to an atmosphere. So I thought the ability to hold on to an atmosphere is a good kind of line in the sand to define a dwarf planet. But I'm going to kind of steer away from defining a dwarf planet specifically and just go either it's terrestrial or it's gas. And then whether or not it's actually classed as a dwarf planet will come out as we build the specific details for the terrestrial planet. So obviously if the mass is below a certain threshold, we class that as dwarf and be done with it. But even the dwarf planet might have an icy mantle, which is something else we need to calculate as part of this. And the whole point of all of this, of course, is to set the scene for generating the life on these worlds. I was a proponent for keeping Pluto as a planet for an honorary sake. But since I've been studying star systems and looking at how they form and everything like that, I do agree that Pluto's not a planet. It didn't clear its orbit. It is sort of a trans-Neptunian object. It's part of the Kyper belt. It's not a planet. I mean, you could make an argument for Ceres being a planet. I'm not sure how you pronounce Ceres. Is it Ceres? Ceres? But mass-wise, it's tiny, so technically it's not a planet. It's a dwarf world. But you've got this grey area between being able to spherize. So you've got that hydrostatic equilibrium where the planet can become a sphere under its own mass. And then you've got another cutoff point where it can start to hold on to an atmosphere because there's enough mass to be able to do that. So I think that spectrum is kind of the dwarf planet spectrum. That's how I class them anyway. I quite like that idea, El Johnarino, yeah. The Neil deGrasse Tyson Planetary Observatory. Yeah, Mal, so with the core mass accretion, and this is the only part of this kind of stack which I'm still not entirely happy with. It's quite simple. So we're doing a random pool of 1% for weird objects, so things like super tiny dwarfs. So 99% of the time it will just be a typical planet. But we've got this weighted curve as to how likely a planet will have over 10 Earth masses based on its position in the circumstellar disk, which looks like this. And so over here we've got a Kelvin value of 700, and anything beyond that is 25% chance. So that's the baseline chance of a planet becoming a gas giant. And then as you move up towards the frost line here at 150 Kelvin, the chances dramatically increase because all the volatiles, all the ices are blown out towards the outer system by the solar wind. So the chance of becoming a gas giant dramatically increases at this point. And this curve kind of defines the percentage chance of the rocky body going beyond 10 Earth masses. Which is a little counterintuitive because you'd expect rocky mass to decrease in quantity the further you get from the star. So it's a bit of a bit counterintuitive. And in the same time, so we have a curve for the distribution of planets with mass below 10 Earths. So you've got 10 Earths at the top here, and then 0.021, which is around about Titan. And this is the distribution. So 50% of the time, it's going to be about 2.5-ish Earth masses, which is roughly in keeping with the fact that super Earths and mini Neptunes are the two most common planetary types that have been found so far. And again, with the 10 plus Earth masses, again we just have a smooth curve, and 50% is about 11 Earth masses, and then that goes up all the way up to 20. It says 10, but it's actually 20. I think that's just a display bug, because you can see that this line is definitely 20, and if you click the point, it is definitely 20, and yet it says 10. So I'm not quite sure what's going on there. But I wanted to weight the distribution so that, you know, super high rocky masses are relatively rare, whereas kind of 10 Earth masses is kind of the norm for gas giants. Yeah, it's definitely a rabbit hole, and I think I definitely think this can be improved further. You know, using curves rather than just baseline randoms, I think, is definitely an improvement, because we can actually distribute the percentage chances along that curve smoothly, which is nice. But the thing about it that I'm not quite so keen on is the fact that we are still doing a random pool as to whether or not a planet is a gas giant. And yes, that is driven by a curve, but still we're flipping a coin. You know, is it a gas giant or isn't it? I'd like something a little bit more organic than that, rather than the coin toss. But I think it's about as organic as it can be for now. So one of the issues I was struggling with is the fact that generating the data for the terrestrial worlds needed to happen in a different order to the data for the gas giants, because with terrestrial worlds you need to work out the escape velocity in order to calculate what kind of atmosphere it would have, because atmospheric elements all have their individual speeds, and if they are above the escape velocity of the planet, then the planet cannot hold on to that atmosphere made of that particular chemical. So in order to calculate the escape velocity, you kind of need the final mass of the planet. But then you can't do that for a gas giant because we haven't actually calculated the gas envelope yet, which of course affects the final mass. So you've got this kind of chicken and egg scenario where you need data before you've generated it. So my solution to that is to simply just split them and do them differently. So we do our base core rocky body first, which every planet has a rocky core at some point, and then we build upon that rocky core to form a more specific planet type. And that's going to be driven by its temperature, its position in the star system, and how much gas it can accrete. Yeah, it's definitely a brain twister, this one. I think I've spent more time on this system specifically than any other system in the game, because it's just rabbit hole after rabbit hole. You think you've come up with a nice solution for something, and then you realise there's another 10 layers of complexity underneath that. And it just keeps getting deeper and deeper and deeper. Yeah, well, on the subject of moons, actually, I've changed the data structure there as to how we store these planetary bodies. No, that's the wrong one. What am I after? Where is it? Oh, there. So we still have this messy graph at the end here, where we're just combining all of this stuff together into its various struct arrays. But something we have now is object ID and parent ID. Now before, I had an array of structs, and each planet had an array of objects that they could be child of it. But you can't have a struct be a child of itself. Obviously that messes everything up, so I'd have to make a separate struct for each child object. And then, you know, obviously when you've got multi-star systems, you've got children of children of children, because you've got the berry center, then a star, then a planet, then a moon, and then maybe a moon of a moon. A moon, I think we agreed to call them. And because you don't quite know beforehand just how many child objects there are going to be, you don't know how many different separate structs you're going to need to make. So in order to make it a lot more expandable, we're just going with a simple object ID for the parent ID, and then object ID for the actual child. So what should happen when the system starts generating the actual star system around the ship? For every object ID that is a child of a parent ID, it will use the location of the parent object as the barycenter, essentially, for that next object that's being generated. Hopefully that's a nice clean way of doing it, and we don't need to use lots of different structs, because we can use the same struct which contains all the data we need, whether it be a moon, a planet, a star, a moon of a moon, a barycenter of a dual star rotating around a central star. We can use the same struct for all of those different scenarios just by managing the object ID and then its parent ID. I hope. It works on paper, we just need to make sure it works in practice. Yeah, like a binary tree. So that should allow us to have any number, essentially an unlimited number of child objects, all the way down to moons of moons of moons if we need to. Including like stations and things. Yeah, that's part of the challenge, is building the ID structure. So with a simple system where you have a central star and then planets, it's easy because you place the central star object, and that has an ID of, say, 0. And then the first planet becomes 1. And then its moons would be 2, 3, 4, 5. And then the next planet would then be 6, and then its moons would be 7, 8, 9, 10. And you could go on like that, so you could just increment numerically as you go. It doesn't need to be an integer, to be fair, it could just be a string. So we could make it a little bit more human readable and have, so the stars are A, B, C, D, E, F, G, and then each planet around that particular star is like A1, A2, A3, A4, and so on. So that there's a couple of different ways we can do that. The naming convention for the star systems will definitely be using that. So in the example there, A1b, so A1b is a moon, is the second moon of the first planet in the system. So the moons would be lowercase alphanumeric. Yeah, I think systems like that one, where you have a planet which is literally swapping between stars, is not something we would include, at least not anytime soon. I think that's pushing the realms of easy coding to extremes. I mean, it's going to be hard enough when we have, say you have 2 stars orbiting a common barycenter, but each one of those stars has its own selection of planets. You need to make sure that you're drawing a cutoff to the orbital distance of those planets, because at some point the orbital distance is going to combine with the other star. I guess you'd use the Hill sphere to define that, but there are lots and lots of complications once you start adding multiple stars, especially when you have like 2 sets of binaries orbiting a common barycenter, because then you've got 4 stars to worry about. Yeah, Elite Dangerous has got some absolutely mental star systems. Yeah, upwards of like 12 stars there. Some of them are crazy. I don't think we'll end up with star systems quite that mental, but we'll have to see. Yeah, I'm pretty sure you could have a pair of binaries orbiting a common barycenter with each of those stars having its own planetary system, I guess, you know, the hill sphere of each star is going to sort out what can be where. And if the hill sphere is, I guess, less than its Roche limit, then it can't have planets. But that's going to be a fun one to experiment with. Anyhow, so what I need to get my head around now, and bearing in mind that I'm going to remove the dwarf option from here, so it's just terrestrial gas, is I need to think about the order in which things are being generated, so that when we come to generate the surface conditions with a view to putting life there, we have absolutely perfect data for the surface conditions of the planet. So we have our base rocky body. Let me calculate our gravity and our escape velocity. So then, armed with that, I guess there we'll do our atmosphere. And specifically, that's a terrestrial atmosphere. That's really cool stuff. It's you know, one of our absolute desires for the game is for people to learn from it and actually start to love astrophysics through playing the game, because it is absolutely fascinating. And one day I'd love to do a PhD in exoplanet systems and just exoplanets generally. I think that's where my focus is. Sorry, I think Claire's just coming to feed some pigeons, so you might hear some interesting squeaking noises in a minute. Right, so let's take a look at this. So that's wrong. Fill that in later. Right, so that is working, so we know the escape velocity. She's just so excited to be feeding birds. The question is, do I define the final planet after doing that, or as part of it? Yeah, I might actually go ahead and do that as part of that tree, because kind of keeps it all in one place, which is nice. And then determining the final planet type is going to have to be duplicated as well, because the list of terrestrial planet types are of course different to the gas giants. And for the gas giants, so we don't need that. So really, we probably need to do the gas accretion first. Don't need those, don't need that. Wait a minute. Explode that. Okay, so we can tell it it's got an atmosphere because we know that for a fact for a gas giant. So again, we're using a curve to do the runaway gas accretion, and on this particular curve, this is the amount of volatiles that exist in the protoplanetary disk. So again, as you move away from the star, the number of volatiles increase. And where are we? So 150 somewhere. It's kind of like almost M-class, sorry, not M-class, Y-class star kind of masses. However, because we want to be able to have gas giants up to 13 Jupiter masses, which is kind of what this is. So at 50 Kelvin, you've got 13 Jupiter masses, which is 4,000 odd Earth masses. However, you don't want that on an M-class star, because the protoplanetary disk on an M-class star isn't going to have anywhere near the amount of material needed to make a 13 mass Jupiter. So we use a mass of base object, and then we put a multiplier on that based on the mass of the rocky body itself. So if the rocky body is fairly small, i.e. 10 Earth masses, then we halve the amount of gas accretion that occurred. Again, this is quite an arbitrary value. Yes, it's based on scientific principles, but it's not based on any particular study in terms of its numbers. So that is winging it a little bit. So this is an example of one of the things which needs refining further down the line, so that we have slightly more reasonable numbers for things. Yeah, the principle is sound. The further you get from the star, the more volatiles you have available to do runaway gas accretion with. You know, the science is sound with that. The grey area is just how much do you have. And I might, rather than using, or maybe even in addition to using the base mass of the rocky core, we actually take a look at what we have available in the protoplanetary disk and stick a multiplier on there as well. So, for example, Jupiter accounts for 71% of the solar system's mass in terms of all planets. That gives us a kind of a ballpark at what a maximum value could look like. Obviously, no single planet can use more mass than is available in the protoplanetary disk. Right, so really that's it for the runaway gas accretion. think I'll move this further down the stack. So yeah, so it's kind of in here really. So we need to take the mass of the atmosphere, we need to add that to the mass of the rocky body, and that's the overall mass of the gas giant. Core plus gas envelope. We do need to deduct that from the protoplanetary disk, but let's just probably do that last. Just steal it from this node. Deduct mass from disk. I could do this up here, but it kind of feels neater to do it last. Okay, so we've got a final mass, which means we can then calculate the radius, which is not from this, because that's for rocky planets. Means that that is no longer relevant, so I shall write something useful there. And that is the wrong thing. Density. I have a suspicion I may have misnamed a couple of these. Right, so that's our gas accretion. Okay. Which is what we want. And our final mass is that plus that. Gubbins go over there. So, in order to calculate the volume, I believe we need the density. I think we need radius, don't we? So that's wrong. Where is the one I did earlier? Was it that one? No, it wasn't that one. I wouldn't go quite that far. It's a pretty shoddy universe. Just going through all these collapsed graphs a minute, because I've been duplicating them, kind of renaming them, and that's not been particularly helpful because I've not been naming them what they should be named. Right, so this is the one that we need to work on soonish. Oh, that's weird. No matter, I shall just make a new node. Because I actually made a couple of handy macros to work out some of the gas giant stuff, and they were embedded in a graph, but I must have reused it for something else, so I'll just make another one. Right, so when doing the radius, so that's got density on it, and so that was volume. Right. What are you? Your volume as well. Yeah, so that's correct for volume. Your density. Right, let's see what's going on there. Yeah, I've obviously I've named things wrongly somewhere and it's confused myself. So right, so radius is the density one. Density. Because I can't name them the same. Right, so volume is volume correctly, so you're good. And you are also volume. Are you identical? Yes, you are. So I've obviously duplicated that and then got myself confused, so that can go away. This is why you don't do things when you're half asleep. Right, so we can't work out the density without the volume. So that needs to come after the volume. However, we need to know the radius, and we will do that from the mass and the density. Right, so that's our final mass. At the risk of further confusing myself. Right, let's name it quick so I don't get confused. So this one is radius. And then to work out the radius, I was listening to an interesting podcast a few weeks back, and they were talking about simulation theory. And one of the incredible arguments against it, which I think is the one that Neil deGrasse Tyson is now sort of clutching on, is the fact that every layer of the simulation requires an equivalence of computational power, and there's only so much computational power available. So if say I'm making this game, and say I make NPCs in the game which are so advanced and driven by AI that they decide to make their own game within the game, but then that's using the computational power of whatever system is running the base simulation. So if their simulation also then decides to make a simulation, you're still relying on the base computing power of level 0. And as that goes down and down and down, you're putting more and more pressure on the base level 0. So it would get to the point where you just wouldn't have the computational power available in order to run those simulations. Now, I think there are counter arguments to that, in that the scale at which something simulates, or the time scale at which something simulates, doesn't have to be linear. So, 1 second could take an hour in one of the deeper simulations without any noticeable difference if you're in that simulation. But yeah, I thought it was an interesting counter argument either way. Right, so we want radius and mass and density. So we have our mass. Where is it? Search for it, that'd be quicker, wouldn't it? So final planet mass, and the density of gas giants is usually around about that. So that should give us our radius. Now this density value here is another one of those things which needs to be determined more organically. So obviously that's the density of Jupiter, and Saturn has a density of like 0.9, something like that. I think it's 900 kilograms per meter cubed, so it's actually lighter than water. It would float. And there's obviously quite a range there, but then you've got like Neptune and Uranus have different sized cores and different densities, but the densities don't align equally with the core size. So I can't take the size of the rocky core and use that as a scalar to define like what the density of the planet would be. It's frustrating to say the least. So we need some kind of organic, intelligent way of defining density without just rolling a dice on it. Though I suppose for now I will just roll a dice on it. Let's get our random stream. So if we were to go, say, from 900 to 1500, which is just literally an arbitrary decision, that should give us a range of gas giant densities. Because again, you've got Saturn has a lower density than Neptune and Uranus, and obviously it's bigger. But then Jupiter's bigger again and has a much higher density. So there isn't a linear relationship between everything that you could base it on. Yeah, for sure. The solution that I like is to use the rocky core to determine some aspect of the gas giant, so that the bigger its rocky core, then the more gas it's accreted into its gas envelope, and therefore the more dense it should be. Although Saturn's a weird one with its really fluffiness. Right, so we've got our radius now, which means we can work out our volume. And because we've got our volume, we can work out our mean density. So the mean density of the planet should equal whatever we decided here. In fact, I'm going to manually set that actually, just so we can test it. In fact, I'm going to set it to something weird like 1288. So if this mean density is calculated as 1288, then we know that all the math is adding up, because it's working backwards in order to derive this value. Right, so we've generated our gas envelope, we've added that to create the final mass, we've then used that to get the radius, which has given us our volume, which has given us our mean density. So having known those things, I guess the next thing we need to do is the atmospheric composition of the gas giant. So I'm going to copy that one. So yeah, this is another one of those instances where the question becomes, where is the best place to do this? Because different materials have different densities. So if we were to do this here, then we're obviously affecting the radius, because it would be affecting this value. Yes, Salaf, that's correct, it should be. But one of the people we're recruiting for is a volumetrics specialist, so we want a shader artist that specializes in volumetric effects, because we want fully volumetric cloud layers and gas giants that you can fly through. So that's going to be, a huge part of the game loop. Obviously, we're using gas giants to refuel the ship, so the experience of flying through a gas giant should be like epic every time. Yeah, I think this does actually make the most sense. So we know that gas giants are predominantly going to be hydrogen and helium, and there should be some variables that I prepared earlier. Did I only do the surface ones? I did actually. So we want hydrogen, and these need to be dual purpose, so we need like non-gas giant common chemicals as well. A table somewhere, so we can find it again. Okay, so we've got hydrogen, helium, methane. Ammonia. Claire's just brought me a cup of tea, isn't she lovely? So a lot of the gas giants seem to have hydrogen deuteride. Pretty sure what that is. Methane. Seems to be the major ones. I'd written down somewhere actually. What was it there? Oh, okay, no, I did it for the terrestrial ones. I wrote down the composition of the worlds just to make life a bit easier, so we know what's on them. Yeah, planetary rotation is something that should get calculated here. So when we're doing our orbital characteristics, rotation should be one of these. I think I'm actually setting it manually on all the Sol planets. But yeah, it's definitely going to be one of the data points. I'm going to borrow that node, I think. I'm going to just write down what's on the other planets in terms of their atmospheric composition. These long comments are not working. Right, so should be 89.8, give or take 2. And then helium 10.2. 2. I'm going to write these out actually, otherwise I'll forget what they are. Helium, methane, ammonia. Okay, so that's what Jupiter tastes like. Yeah, you're right, it does. I'm getting this data from the teachastronomy.com website. They need to go to teachmath.com. Hey BC5. I'm currently doing atmospheric compositions, where I am rather excitingly copy-pasting numbers from a website. Fascinating looking at the values of the gas giants in our system, and how just the small differences make a big difference in how they present physically. It's like, Uranus and Neptune have less hydrogen, more helium, and physically look very, very different. However, there's very little between them, really. I wonder who the first person would be to sniff Jupiter. I'd take that honour. I think for now I'm actually going to group all these other chemicals just in other. Going to need oxygen and nitrogen in this lot as well, aren't we? Yeah, Peter, that's a fair point. But I think, at least for now, we'll keep it simple. As we build out the system, we can go deeper with it and start really going into crazy amounts of depth in terms of the depth of data we generate for gas giants. I think for now, we'll just do an average by volume, which is kind of what these numbers represent. So sort of by weight, Jupiter, for example, is almost 90% hydrogen. Or at least it is according to teachastronomy.com. Just wondering whether I do a temperature factor on this. Yeah, the color of a gas giant is very much driven by its temperature. So the temperature defines what clouds will form in the upper atmosphere of a gas giant, and it's the clouds that you see which give it their color. So if you were to move Jupiter into the same temperature range as Uranus or Neptune, Jupiter would be blue, as evidenced by the fact if you look at its poles, they're blue, because it's very much that's what the cloud formations are like in those temperature regions. So the system that we'll be making for the game, hopefully will have a very, very organic line of temperature values and different cloud compositions depending on those temperatures. So you'll get a huge array of different coloured gas giants depending on what their equilibrium temperatures are. And that's all down to the chemical compositions. So I think what I'll do is if I do take our random stream again. So get float in range. That's not how you spell float. Should I random flow in range from stream? That's what I wanted. So just off the bat to begin with, we will do. Let's go from say 95% hydrogen down to 75% hydrogen. Again, that feels like it should be driven by temperature. Yeah, I think pink clouds is definitely possible for gas giants, and green clouds are possible much closer into the star system because you actually have alkaline metals as clouds. Does Saturn really have that little amount of helium? So this is another typical example of what it's like when researching this stuff. Apologies for blinding everyone. So you've got 4 websites here. I'll make it 5. All of them give you a completely different number. It's like, how are they all so different? I mean, surely the data is coming from the same missions. You know, NASA's only sent so many probes in Saturn's locale, and you know, we've only got so many times that James Webb or whatever has been pointing at Saturn. So how are they all so different? I think I'll just take an average. So according to the European Space Agency, Saturn is 75% hydrogen and 25% helium. According to Wikipedia, it's 96% hydrogen and approximately 3% helium. And Space.com says 7% helium. Yeah, it is the complete lack of any correlation, depending on what reference you look at, is very frustrating. You'd think, you know, as a species, with all the scientific instruments we have, you'd think we would know fairly certainly what the chemical composition of Saturn is. At least with a small margin of error. Right, so if we take our hydrogen and our helium, and I'll make that from 5 to 25. Hang on, we're going to get over 100 here, aren't we? So the maximum value has to be 100 minus that. Minus an additional need to make sure we've got enough room in this mass distribution. So we need to make sure we have remove that from our 100%. remove at least another 1% for whatever's left over. And then methane is around about 0 to 1, 0 to 3, let's say. So we go from 0.01. Now, normally I would say 3, but yeah, I've watched quite a few of Dr. Becky's videos, and I have contemplated contacting her and seeing if she wants to get involved. Make that range just a little bit bigger. Right, so that's only going to leave us 3 if it hits the maximum value. Which means we need to fit these ones. So really that needs to be... I suppose it can stay as 0.1. It's going to have to start at 0, I suppose. Yeah, I'll stick with 0. So we're really squeezing this in here. So if we hit 97%, then there's only 3% left over for helium. But we do want to kind of reserve an extra percentage point for other stuff. So really want to, yeah, so we want to take away 2 there and just the 1 there. And then the final 1% of the planet's mass is going to be other stuff. So really we need to make an other. That needs to be those three. Actually, I might be able to do this slightly more intelligently. So we want 100 minus them, and whatever's left over is our other fraction. So when all's said and done, this should add up to 100. He says optimistically. We're leaving at least headroom of 2% there, headroom of 1% there, which definitely leaves at least 1% for everything else. Okay. So that should be our gas giant's atmospheric composition done. At a basic level, anyway. So I suppose the next question is, what about life forms which are prevalent in the upper cloud decks of gas giants? I think we should have it. The question is how to implement it. Definitely need to go off of the chemical composition. Like Jupiter, for example, it has a percentage of water, however small that is. You know, that could be an indicator for life. Also average temperatures as well. I'll have a think on that one. In fact, I'm going to make a note for it. Hey Geodiosity, welcome to the stream. Ooh, I get to use my life boolean. Where is it? Ooh, I haven't even made one yet. Oh yeah, I saw a photograph of that sulfur node. There you go. Something for the next dev build. We'll have 10% of gas giants have life on them randomly. Obviously that's not staying like that, but fun test. Right, so let's just take stock a minute. So we calculate our runaway gas accretion. What's this one? So let's deduct the mass. So I'm going to grab a copy of that. Just make sure that's sure we just have that ready. Right, so runaway gas accretion done. We work out our final mass, which is really, really simple in this case. We then work out our atmospheric composition by just randomly flipping some dice. We randomly decide if there is atmospheric life. And we then work out our radius value, which gives us our volume. And from that we can work out our mean density, which of course we already know because we specified it here. But they should match, and that's a good way of checking itself. So knowing all of those things, we should be able to build our final planet type. And then it's our last act. Deduct that mass from the disk. Yeah, and then construct the planet object, which do we want to do that separately? I think so, because some of this stuff is not relevant to gas giants. Okay. Let's draw a box around it. Well, fingers crossed this is the full stack needed to generate a gas giant, and then nothing else other than that should be needed. Hopefully, at least. Just make sure we're deducting the mass. don't need to do that bit because we've already got our final mass. It's a simple node, but it does the job. Right, so we can delete that. And hang on, before we do delete that, do we have a copy of it? Yes, we do. So delete that one from there. And delete that one from there. Why is it all the way over there? Right, so finally, this is where we define the actual type of gas giant this is. Okay, so equilibrium temperature for 1400 is a class 5, 900 is a class 4, 350 is a class 3. So Waterworld's an interesting one, and I think I'm going to get rid of that for now. And I'll focus on terrestrial Waterworlds. But we do need to roll non-terrestrial Waterworlds into the mix here somewhere. Saturn's Kelvin 135, and Uranus is right. So if we make a cutoff. So I'm just thinking we need to just get the ice giants into here for now. So we're over 100. We're over 100 Kelvin. We'll go for our class 1s. Otherwise, they're going to be ice giants. So we want to, again, over time, really expand this list, because this is a relatively vague definition for the different gas giant types you can get. Basing it on their Kelvin value is a good start. At least it gives us a broad idea of the type of gas giants that there are. But this needs to be way, way, way more granular, and there need to be sub-steps between these classes. So we're using the Zadarsky scale for gas giant classifications. The Zadarsky scale doesn't have ice giants in it, interestingly. So I think we'll probably make our own sort of derivative of the Zadarsky scale, and have some subclasses in between these, and that will give us more scope for doing cloud layers based on temperature zones. Right, I think that's it really. That's all we need to do there. Right, let me just double check this again. So gas accretion, check. Final mass, check. Atmosphere, check. Why am I saying that? Oh, actually, do I do it there? No, I will do it there. Let's get rid of that because we've already specified it. I want to duplicate our efforts. Leave that focus purely on composition. Random ball for life for now. Radius, yep. Volume, yep. Mean density, yep. Final planet type, yep. Deduct the mass from the disk, yep. And then put it all together into a large system object, yes. Okay. Right, so I think that's actually gas giants done. Next up, there's the arguably more complicated terrestrial worlds. Did you? Oh look, I missed out gravity. Oh. What are we calculating it from? So we're taking it from mass and radius. So we'll maybe pop that. Well, actually, on that subject, we may as well do escape velocity as well, because we don't need escape velocity to calculate anything for gas giants, but if we've got it, we may as well report on it as a value, because, you know, it's a point of interest. And what we're using, mass and radius. There and there, so that's fine. I need to add some data points for things like escape velocity, because we don't have that in the data yet. So hopefully that's all the sort of the pertinent information that you'd want about a planet. The only thing I can think of that we're missing from here is the fraction of the core versus the overall radius. Like what percentage of the radius is the rocky core? I can probably work that out from the densities. Yeah. I will add that at some point, but not now. Right, now for terrestrial planets, things need to happen in a slightly different order to all of this, because first of all we need our gravity, and what are we using? We're using final mass, so it's not the one we need at this point, so I suppose we replace that with rocky body mass, because that's the mass we're working with. We should already have our radius from here. That's something I could do actually. I could just add that radius to that one. I'll have a look. So we've got our mass, radius, and gravity, and the escape velocity. Final planet mass. So do we? I guess the atmosphere is going to be such a small percentage of the mass as to not really make much of a difference. What percentage of Earth's mass is its atmosphere? Okay, so the atmosphere of Earth is roughly 1/1,000,000th of the Earth's total mass. So I think on that note, we won't need to include it as part of the overall mass calculation. So we do then, however, just need to do the final mass, which should just be that. Yeah, so that's fine. That. I know it's kind of pointless making a collapsed graph for this, but it's really just there for aiding in sort of understanding the flow of how we're calculating things. Which means we will actually take our final mass there. So we convert rocky mass to final mass, we work out our gravity, work out our escape velocity, and then comes the fun bit, which is working out the atmospheric composition. So I suppose we need a table showing the atmospheres of the sole terrestrial planets. I wonder how accurate this image is. So this is handy. It's fascinating that Mercury's atmosphere just has that percentage of oxygen in it. Not that it would help you very much when the pressure is practically zero. Okay, I'll use that as a rough guide. I should actually have a bottle of Gentleman Jack, which we were going to buy on Prime Day recently because it was like half price. I thought, ooh, bottle of Gentleman Jack for half price. I'll have one of those. And then Claire forgot to press checkout, so we didn't actually get it in the end. Earth. So by weight, surely there's a nice table somewhere I can use. Alright, fine, I'll use the image. Right, so 78% nitrogen. Oxygen is 21%. I'll keep doing curly brackets. Argon is about 1%. Monoxide or dioxide? No, it's dioxide. Don't want to be breathing that. Nitrogen percent. One percent other gases. Quite a simple atmosphere, really. It's Mars, so similar quantity of carbon dioxide, actually. Why can I not spell dioxide? There we go. That is 5%. Roughly 3% nitrogen, 0.5% argon, about 0.5% other. I'll stick mercury on there as well. It's interesting that mercury has so much oxygen. And oddly enough, sodium. I'll also add the other trace elements. So we've got helium, krypton, argon, CO2 in there, some water, and 2 is xenon. What was that? Krypton. But any is. Venus, what do you have? So, some of that, some of that, some of that, some of that, and some of that. The reason I'm making a note of these is just so that you kind of have a broad spectrum of the type of chemicals we expect to see generally in exoplanet atmospheres. Obviously, hydrogen and helium I would expect to feature fairly heavily because they're what stars are made of. And finally, Mars. Yeah, so if we consider that sort of the broad swathe of different chemical compositions that there could be, kind of need a table of escape velocities to rule out ones that couldn't possibly be part of the atmosphere. Obviously, the first point of note is that gas giants are massively hydrogen in their makeup, and the terrestrial worlds have barely any. Yeah, I think the similarity with Mars and Venus is down to volcanicity. So I think that carbon dioxide is all going to be from volcanicity. Yeah, absolutely. So one of the things that's been raised as an issue just from testing with the galaxy is that there are planets with atmospheres which couldn't possibly have an atmosphere because of the temperature that they're at. So we kind of need to know what is the maximum temperature that atmosphere is supported. So on that note, search. I actually found the value for this yesterday or the day before. I didn't actually write it down, which is frustrating. We know we want to base this off of an equilibrium temperature. Okay, so we're looking at around about 1,000 to 1,500 Kelvin for a planet to just not have an atmosphere, on geological scales at least. Right, so we need to work out the thermal velocity of gas molecules. So we need a table. Yeah, I found a table with combined chemicals. That's no good. Okay, so well, it's interesting actually. So hydrogen and helium have really, really high thermal velocities at 1700 meters per second and 1200. So if a planet is fairly small with an escape velocity less than 1700 meters per second, then it literally cannot hold on to hydrogen as an atmosphere. It's kind of fascinating. It's facts like that that I find interesting. Hey Team Ruddy, we're working on planetary atmospheres today. We've just done the gas giants, so they're all done. And now we're doing terrestrial planets, which is more complicated because there are more factors at play. So we need to write down the thermal velocities of various gases, and here's a table I prepared earlier. We don't want that in freedom units. Right, so that's a rough idea of escape velocities for those. So what's Earth's escape velocity? I thought it was like 11.2 kilometers a second, I think. Escape velocity 11.186. Kilometers per second. May as well do the others while we're at it. So Venus is 10.36. Kilometers per second. Imagine Mercury's is probably quite low. 4.25. See, now I'm interested as to what oxygen's thermal velocity is, because there's a lot of it on Mercury. Well, as a fraction, I guess there's barely any in terms of actual amount. But you'd think with hydrogen having an escape velocity, what's that? It's 1.7 kilometers per second. Oh yeah, so it can hold on to it. Yeah. Interesting. And then Mars. 5.027. Austin, thanks for that. Glad you're enjoying it. And so the atmospheric data is going to be procedurally generated for practically everything in the galaxy. For the Sol system, it will all be manually entered into the data. And indeed for backer systems, the in-game tool that we build for building the backer systems will allow you to enter these values manually. Again, it will enforce limits to make sure everything adds up to 100%, and that the escape velocity of the planet is greater than the thermal velocity of the chemical. Yeah, well, once the planet's been created, we can simply give a list of valid materials based on their velocities. This was thermal velocity, wasn't it? Yeah, for sure. Yeah, so these are at room temperature. Okay. And oxygen is how are you? Okay, so we take our rocky body mass. Do you remember? We've got a final mass by now, haven't we? Right, so if the final mass is lower than, although that having been said, what we're using to calculate that with, so that's mass and radius. Just need to try this calculation out of interest with Titan. the radius of Titan? 2,500 kilometers. Teeny tiny. Okay, so the moon Titan has an escape velocity of 2.6 kilometers per second, which means technically it can hold on to these chemicals. Which would explain why it has such a thick atmosphere. Yeah, good point, Team Ruddy. Ah, well spotted, Zelaf. No, you're right, that shouldn't be 0. That makes no sense whatsoever. Where's my spreadsheet? Should be 0.5. Yeah, it's a square root essentially. That would have mucked it all up. Yeah, so you're taking the square root of this, and that gives you the escape velocity. That's an interesting observation, Ian. I hadn't actually thought of that before. You're right. Yes, that the plasma generated on re-entry is going to be chemical dependent, so you go up in a big pink ball of fire. See, now that I know that, I'm going to make an effort to model it. So we're going to need a list of different chemicals and what colour they burn. Right, so let's start reducing this mass a little bit. So what's the moon's radius? Let's go with that. And the mass of the moon is what? 73 with lots of zeros. And that's interesting. The escape velocity of the moon is pretty much similar to that of Titan, despite being half of its size. Right, so first of all, if we assume the temperature of which a planet will burn off its atmosphere is 1000 Kelvin. Then we definitely do not have an atmosphere. That's an easy one to work out. And then we need... Oh, wrong way around. Actually, we're doing OR in here. So OR, if the mass of the planet is less than... What value was I using? I was using about that, just about just shy of double the moon's mass. So really, if either of those are true, then there's going to be no atmosphere realistically, because they just don't have the mass and the temperature's too high. Right, so that's an easy one, and of course the atmospheric mass is 0. I'm going to have to use the mass fraction, i.e. the fraction of Earth's mass, to work out global warming. I might be able to do it just with the raw kilogram value. So I will see when I get to it. The planets do already rotate. Yeah, something I took great pains over when sorting out Mars's atmosphere was to make sure that the sunset on Mars is blue, because of the air density with the sun shining through the atmosphere reaches similar levels as to the density of the atmosphere looking straight up at midday on Earth. So you kind of get that crossover where the atmosphere is actually blue on Mars at sunset, which is fascinating. Yeah, I definitely do want the atmospheres to have atmospheric scattering based on their actual chemical composition. So like the Rayleigh scattering and that sort of thing. The trick is knowing what the values should be. Obviously, we can make the atmosphere any colour we want quite easily, but we have to take, the chemical composition of that atmosphere, like, let's say carbon dioxide. Wouldn't it still just be blue? Wouldn't it reflect blue light? But that's an interesting rabbit hole again. If someone has a nice list of all the different chemicals and what their atmosphere colour would be, that would be very handy. Right, so it also needs to be 0. It's just reminded me I need to set that on here. So when we do the atmospheric composition, we also need to make sure we set the atmospheric opacity to 4, which is sort of equivalent to Earth. That's just for the shader that draws the atmosphere. El Johnorino, yeah, for sure. I mean, that's one of the fascinating things about this. Once we've got the sensors UI fully populated with all of this data, then immediately that's educational, because you get to see the relationship between all these different values. And when you're out there exploring the galaxy and you're coming across these exoplanets, it's fascinating to see the distribution of the chemical compositions and how the volatiles get pushed out away from the star, and all those astrophysics principles, which for the average person they've probably never even thought about it, and yet through playing the game they naturally kind of just learn that just through playing, and I think that's really cool. Like we're forcing astrophysics on people. Right, so next step. I think I'm going to go by radius and maybe use that as a weighted curve. Yeah, one of my absolute dreams for this game is to see like an astronomer teaching a group of students within the game. So like the astronomer would be the captain, the students would just be milling about the bridge, and the lesson would take place fully within the game environment, where the astronomer is giving a tour of the solar system and maybe some exoplanets, and have it be fully properly educational and accurate to science, where people actually genuinely learn something. I think that would be really cool. Some of the astrophysics we are sidestepping. So like with the galaxy structure itself, we're not going to do a fluid simulation to build the galactic structure. However, we are using other people's research on what the galactic structure actually is. Things like the Gaia data and stellar scans, and we've got some really accurate models of the galaxy, so we'll be using that data to build the galaxy, but we don't need to go through the process of doing the actual fluid simulations to work out where the open clusters would appear. So for things like that, we will procedurally generate the open clusters where we know they should be, which is sort of on the leading edge of the spiral arms, where all the gas and dust condenses because of fluid dynamics. But we can do that without actually having to simulate it. Yeah, I do want to include a whiteboard actually. I think that would be really cool. I mean, everyone's going to draw penises on them, but still, I think they'd be cool. Yeah, the FTL effect actually does do redshift and blue shift at its sort of leading and trailing edge, just as a visual effect. But I'm torn on this because I'd love to render the space beyond the ship whilst you're at FTL as what it would actually look like, which would be pretty much a mess. But that really removes the cool factor of seeing the stars drifting by as you're flying along. So it's one of those kind of gamification balances. Oh, that's interesting, Leon. Thank you. Yeah, screens is an awkward one because the render cost of having a screen is actually huge, because you're essentially writing 60 frames a second to a texture, and it's crazy expensive on the CPU. Very true, Delta. Right, what was I doing? I was going to make a curve, wasn't I? So if the chance to have an atmosphere is directly tied to planet density, then we need rocky body mass as a fraction of Earth. Get my head around how I'm doing this actually. So if we map range clamped on that, and then we do a random pool with weight from stream, and then the weight for that would be that. Ah, don't worry, Leon, it was interesting. The kind of nerdy stuff we love around here. Okay, so if we take so obviously 10 Earth masses is a guaranteed atmosphere because you're talking gas giant at that point. Then 0% should technically be something like that, which would be check my spreadsheet. Yeah, that's right actually. So that would be just below Neptune, roughly half of the moon's mass. So if we're saying essentially a 0% chance of an atmosphere around something the size of the moon, moving up to 100% chance at 10 times Earth, then that means that 5 Earth masses would only have a 50% chance of an atmosphere, which is pretty unrealistic because you're looking at substantial mass and probably quite a large gas envelope. So yeah, that's gonna need a curve, I reckon. Yeah, I've actually paid for that new project thing that Claude does. So you can actually create a project and use the AI as like a colleague, I suppose, within that project. And I use Claude for just general astrophysics questions and helping with math. The problem with AIs, I mean, even Claude, which is, right now supposed to be the most intelligent one, it hallucinates a lot. And one of the things that I got Claude to do a couple of days back is I got a bunch of science papers on distribution and scale of exoplanets in terms of their mass versus their radius, and some other exoplanet data. And I basically fed all of these PDF documents into Claude and then got Claude to summarize them and to basically pull out the useful bits of all these science papers to save me having to read through them all. And it actually did a fairly decent job, but when it came to actually putting that into action and saying something like, right, give me an equation which we can use to produce a realistic gas giant radius based on its known mass. And that's where Claude falls on its face, because you're getting to the point where the AI has to actually properly think about something and actually do some novel science, and they're not quite there yet. I mean, they're close, but they're not quite there. So everything that I've ever used AI for to date, I've had to go and fact check to make sure that it's not talking nonsense. And I would say about 75% of the time it's talking nonsense. And that especially doesn't help when, like I showed earlier, if you just Google something like, how much helium does Saturn have, you get like 20 completely different answers from what are respected sources, like the European Space Agency and, well, to a lesser extent, Wikipedia. But, these are not unknown sources, and yet they all disagree with one another. So how could an AI possibly give you the right value when the source data that it's trained on doesn't agree with itself? I think AI is a really good helping hand, but it needs fact checking every step of the way. I generally spreadsheet everything an AI gives me, and if it works in a spreadsheet, I run with it. Now, I do agree that the AI is the future, and I think it's what it can do is remarkably impressive. Like, being able to feed science papers into an AI and then have the AI summarize the points of those papers and give me kind of simple versions of the equations and things outlined in the science paper. I mean, it's tremendously time-saving for me to be able to do that, because it means I don't have to read through all these science papers. I can just say, right, here's a 20-page document, give me a 2-paragraph summary of this document, and it will, and then I know whether or not I need to dig deeper. Yeah, for sure. Yeah, that's an interesting point, Javier. It's like with the centrifugal forces of the planet, push the atmosphere out, because obviously the velocity is going to be increased by the planetary spin. So yeah, that's an interesting one. Yeah, OpenAI released like a 4 or 5 point step towards super AI, and I can't remember what the steps were now. OpenAI steps to AGI, I think that was it. Ah yeah, there you go. So OpenAI class it as conversational AI, which is what we've got now. problem-solving virtuosos, which is kind of where we're teetering on, autonomous agents, which is what they want to do next, and innovators and organizational equivalents, which they put as step 5. And I think we're far away from innovators, and it's the innovators level which to me is AGI. So that's where an AI could perform novel science and make new discoveries without human interaction. And once that is achievable, then there's the scientific discovery rate on this planet is going to go through the roof. Because you could just throw like the Alcubierre metric at an AI and say, right, make this work, please. Thanks. Yeah, I've not done much to the ship itself. I've been working fully on atmospheres and planets and everything over the past week or so. I really want to get the life generation side of things done and implemented onto the sensors, and then I can start polishing everything ready for the public build. Kind of on the final steps now. See you, Leon. Thanks for watching. Let's make another curve. So, what's this one going to be? So this curve is atmosphere chance by mass. Right. So we want basically a 0% chance there. And then this would be 10 Earth masses. And the chance there would be 1. However, we want to just drag that out a bit. So at 1 Earth mass, the chance of an atmosphere is tiny, so we kind of need to do something more like this. So what are we on? So to push that even higher. Yeah, so I think that's kind of where I was going with it. So Although, that having been said, it's Mars as a fraction of Earth. Mars radius as fraction of Earth. 0.5. So that is perhaps a tad high. Of course, the alternative to this is we drive well, I guess the proper way of doing it would be to drive atmospheric density and volume, or mass rather, as a multiplier from the amount of mass on the host body. So its gravity and its escape velocity, and work on it from there. Because using an arbitrary curve like this does the job, but you know, how does it match reality really? Because if we're saying 50% chance of an atmosphere at half Earth's mass, i.e. Mars, like fine, but 60% chance of an atmosphere at Earth mass, it's I'm not convinced that's the best solution for that. But to make a better solution, we would have to use the mass of the base planet and kind of derive atmospheric material from there. If you picture my brain as an hourglass right now, that's about right. I'm going to keep that on standby because I think that's potentially a good way of doing it. But if we take I suppose the other question we want to know is, so what is the mass of Earth's atmosphere? Quite a lot. 5.5 quadrillion tons. What's that in numbers? They've written that wrong. They neglected to... that should be 10 to the power 18. That makes more sense. So Earth is that many kilograms. Just going to see whether there's any kind of correlation here. Okay, so Venus has a lot of atmosphere. And Mars doesn't have much at all. That's an interesting point there, Javier. Thank you. So I think the Venus's atmosphere is down to its volcanicity. It's got so many volcanoes on its surface spewing out carbon dioxide that it has an immense amount of gas in its upper atmosphere. So that would explain Venus. So, you know, volcanicity is another thing, to be honest, that we need to factor into all of this, and then we need some way of driving, you know, where that volcanicity comes from, or understanding where that volcanicity comes from, and then we can use volcanicity you know, to help drive some of this. So we have a really highly active planet, volcanoes wise, then, you know, we can spew out a lot of carbon dioxide into that atmosphere, you know, and make it a bit of a Venus-like. Which takes us back to our original problem, which is, how do we organically grow an atmosphere around planets? So we got our hard cutoff. It's more than 1,000 Kelvin or smaller than half of the moon. It doesn't have an atmosphere. Simple as that. Yeah, so we need to grow the atmosphere in line with the overall mass of the rocky body, because the bigger the rocky body, the more of a gas envelope it's going to attract. I suppose so. I'm just thinking. So rather than making this a chance of an atmosphere, instead make it a volume of an atmosphere. Yeah, water's another thing to add to the list, actually, so the amount of surface water and what that water is made of. Right, so if I make this a scalar then, so it already is, that's good. So at our Titan mass, we've got 0 times whatever we decide the volume of the atmosphere should be, up to 100% of that value. If it is 10 Earth masses, we just need to make sure that 0.6 of that value isn't a ridiculous amount of atmosphere for an Earth-like. Because another factor in all of this is oxygen saturation is dependent on pressure. So, like the 21% oxygen in Earth's atmosphere is only good at surface level, 1 bar of pressure. If you change the pressure, then the oxygen value either becomes like too much or too little because of the pressure variance. So we need to take that into account as well when it comes to a true Earth-like world. Yeah, that's a good point as well. We should be able to do the core side of things fairly easily, because we've got we do have the core and the mantle and the crust in terms of densities. So going by the density of the core material and the size of the planet, we can hopefully derive core temperature from those values, and then derive volcanicity from there maybe, and also spin, of course. I believe hotter cores spin more quickly, as I understand it. Yeah, see, moons are a bit of a pain in that regard, because we won't have generated moons yet at this point. It's sort of, in the generation process, because we're still, in the process of generating the primary body of that planet-moon system. So it's not until after we've done this that we actually then start generating moons, because we can't work out the Hill sphere until we've, defined our final mass and radius values. So there's lots of those chicken and egg scenarios where you just need something before you've got it, and whether or not a moon is causing volcanicity or dragging tectonic plates around is something that we can't model because we don't have any moons yet at this point in the code. So, perhaps there's a way of kind of pseudo doing that, or maybe deciding that there will be a moon and spawning a moon based on the fact that the planet needs one, rather than doing it the other way around. We'll find a way of working around that. Right, I think what I'm going to do with this is, obviously we got the hard cut off there, and I think if we're on the positive side of the hard cut off, then the planet is going to have an atmosphere. The question is then how much of an atmosphere. So we're not deciding if there is one, we're defining the properties of that atmosphere instead. Now, if we take this, see, we're almost running that kind of runaway gas accretion task that we would need to do for gas giants, but here instead. That's one of my favourite lines as well, Peter. Along with the whole red alert one. But sir, that does mean changing the bulb. Yeah, I've watched Red Dwarf back to back so many times. Right, here's what I'm going to do. For now, just so we can get this running and tested, because I need to put a build out tonight, so to get this build worthy, why don't we go from, just take our planetary mass, and run our opacity from 0 to 4. So at 1 Earth masses, we will have a fully Earth-style atmosphere, and anything less than that, it will start fading away. Now this is in no way accurate, but will do for now. Yeah, and then that allows us to move on and do the actual final planet type code. Which would be this. Why is that all the way over there? It's funny you should say that, used to be one, because SpaceX in particular are a huge inspiration for kind of how I work. I love their iterative failing forwards approach, and the whole build an orbital class rocket on a sandbank, kind of thing. It's like SpaceX are the Colin Furze of the orbital rocket industry. But I love that, and I love the whole concept, because if you watch any interviews with Elon, he always talks about things like the best part is no part, and I take that methodology into my coding practices. So I always think the best code is no code. So if you can achieve something without having to write extra code to achieve it, then that's always the most efficient path. And that's how I handle optimization. My favorite way of optimizing is literally just deleting code, in the same way that when SpaceX went from Raptor 1 to Raptor 2 and now they're working on Raptor 3, the whole process they've just been deleting parts. Like, no, we don't need that on a rocket engine, we're just going to delete that part, or we'll incorporate that part into the skin of the rocket structure itself. And I love that iteration and that optimization, and I'm constantly doing that with the game, constantly iterating and optimizing. Yeah, absolutely. I mean, simple is best, but also not necessarily the easiest to achieve. Yeah, absolutely. I'm not a fan of complex solutions. I like to keep it simple. Yeah, I think the way I'm approaching a lot of these systems these days is to just do them modularly, step by step, and finding the simple step-by-step approach is easier to get your head around the logic flow, and it's easier to make changes because you're just changing a module, not having to dig through spaghettified code. The biggest challenge for me with this has been getting the order of operation down properly, because there's so much of it that, again, what order do you do these things in to achieve the most efficient way of generating a planet? Because ultimately all this costs CPU, so it's not about just getting it right scientifically, it's about making it performant as well. Because if we don't, like right now, we're not conducting mass, so we had some systems that were generating several hundred planets, and that was locking up the whole game for about 5 to 10 seconds because it's having to do all of this hundreds of times. So that's just another consideration to bear in mind. Right, so hopefully this should capture everything. The rules for Earth-like planets have been tightened a fair bit. So the temperature range is fairly specific, as is the atmospheric density, along with the gravity. Hey Scott, thanks for joining the stream. Yeah, well, I'm hoping to keep the complexity down to an approachable level. So all the complexity is taking place sort of behind the scenes. So when you look at a sensor's UI, and it's giving you a whole bunch of data. The data is there as a point of interest for the most part. It's not really something you need to understand or need to work with in order to play the game. But for those that do find astrophysics and exobiology and all those sorts of things truly fascinating, the data will be there for them to delve deeper. So how deeply you delve into the game's data is kind of down to the player. At least that's the design goal with it. Right. We might be at the point where we can test this, so let's just double check everything. So our super complicated mass calculation there. Then we do our gravity, the final planet mass. And then we work out our escape velocity. Yep. And then we decide if it's got an atmosphere, and if so, how much. Final planet type. So this is where we do our planet density. So for now I'm going to skip that. This is going to need a bit more thinking about. I'm going to try and work this backwards differently, because one of the issues we had prior to me sorting all this out is that gravity readings were wrong because the densities of the materials were wrong. And again, we're trying to guess densities by using mapped ranges. And whilst they're good for approximations, they're not great for accuracy. So now that we're generating our radius and volume from the base body, I'm hoping we can do our mantle, crust and core calculations as a fraction of volume instead. We should make it more accurate. So yeah, then we have our aha. Ha 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 ha. Right, so this one's the same problem we had earlier, where I've named something the wrong way round. So that's wrong. That should be density. So we've got our layer densities, which we'll do later. Our mean density, which is easy to work out. Then we deduct the mass from the protoplanetary disk. Then we construct our planet object. Right. So that should be all of the data points aside from things like surface water, which we're going to have to squeeze into here. Let's run it. In fact, let's do a save all, and then let's run it. And see how hard it falls on its face. Oh, the YouTube player's working again, by the way. I spoke to the author that did the plugin for this, and he's fixed whatever he needed to fix on his domain, so it should all be working again. Okay, step 1. Do we have planets? Yes, we do. Lots of them there. Yes, we do. Mark, no they're not, for the simple reason that the total mass of the Kyper belt is so tiny as to be irrelevant, and the same with the Oort cloud. It's such a small amount of mass that we're just going to add it on afterwards. So the idea with how I'm going to do this is the Oort cloud is going to be a visual effect you see as you're approaching the star. So you'll just see like a misty outline in the shape of the Oort cloud as you approach. And that kind of just gives you an idea of the star's hill sphere, essentially. And you'll just kind of fly through that like you're flying through a cloud. There'll be nothing tangible there to interact with, it's just a visual effect. The Oort cloud, however, the Kyper belt, every star system will have a Kyper belt. I've watched quite a few different videos on how protoplanetary disks settle and how Kyper belts are formed, and kind of like every time a simulation is run, you always get these Kyper belt style objects whizzing around in these highly eccentric orbits, because they're kind of the leftover gubbins from the solar system forming and settling down. So I think it's fair to assume every star system will have a Kyper belt equivalent to a greater or lesser extent. So we're running with that assumption. So every star system will have one. So beyond the last planet, you will have an array of just highly eccentric cold objects, and they'll all be like trans-Neptunian objects, so you know, your Plutos and your Charons, that sort of thing, and maybe a bunch of just asteroids and distant comets, but none of that will take the actual disk mass into account. We use up the disk mass with the last planet, and then we spawn a Kyper belt. So something I've noticed, if the first planet in the system is a gas giant, generally speaking, that's all that's going to be there, and it seems to be mostly prevalent on M classes. So, like that one there. It's not a huge gas giant, it's just shy of Jupiter's mass, but it's big enough that it's munched up the whole of the protoplanetary disk. the same there. You've got this one's slightly smaller, but again, it's completely chewed up the whole protoplanetary disk. And I guess there's a question of realism there, like how realistic would that be? I mean, it's essentially making the M-class stars binary systems, because... And I found this fascinating. I didn't learn this till yesterday, but Jupiter's barycenter with the Sun is actually beyond the radius of the Sun, which means technically Jupiter is in a binary relationship with the Sun. If we use barycenter being beyond the planet's or star's radius as the rule for whether or not it's a binary system, then Jupiter is in fact a binary of our star, which is really weird. But in a situation like this, where you're dealing with, like this one specifically, you've got a planet which is... Which one was it? Was it that one? One of those. Yeah, it's 90% Jupiter's mass around an M-class star, which is significantly less massive than the Sun. So the barycenter is going to be way, way, way beyond that M-class star, which means this is basically a binary system with no planets. And do we want that to be the case? Like here, we have just a terrestrial planet, which means there's enough mass left over for another gas giant. Now, something I did yesterday as well is I went through and added all the comparators for Earth. So when we're sort of sanity checking the data, we can make sure that these values add up. Like, nearly four times Earth's mass, but only 1.4 times its radius. Sounds wrong, but in actual fact is pretty much right. As borne by the volume. Not everything. There's a few things. Well, it depends on the star class. I think it's the M classes that are struggling because they have such a small amount of mass in their protoplanetary disks. Inca, yes, definitely. So I've mentioned this on a few streams, but I have 2 lines in the sand which are preventing a public demo update. Line number 1 is the new ship layout being mostly done in terms of its structural framework. Not the interior detailing, but just the structural framework. And line number 2 is this sensors UI finished and polished with life data being generated for planets. Now, we're getting tantalizingly close to that being done. We're on like the nitty-gritty bits of Planet Gen now, literally looking down at chemicals and atmospheres. That's kind of the final steps of the Planet Gen itself before we can think, right, life, where's that coming from? Our star is a G2V, to be precise. Yeah, absolutely. Those last few percentage points of just polish, you're looking at weeks of polish. See, like you've got. So this particular star is an M4V, which means it's got a relatively small protoplanetary disk. Yeah, it's got a decent selection of planets. But yeah, a tiny one. I've got rid of the scanning animation on here temporarily, so whilst we're going through and verifying data, just so that we can just click through them and check it without having to wait. See, this is an interesting example. So we've got an atmospheric terrestrial planet, and it reckons it's got a mass of 0.2 of Earth. Now we set a hard limit of 0.21 for the atmospheric cutoff. So technically, this should be a dwarf planet without an atmosphere. Because this is a tiny, tiny planet. Practically the size of the moon. And it's freezing. So yeah, I need to look at the mass cutoff there, because that strikes me as being wrong, although it could just be a rounding error on there. Perhaps it's just scraped over the line. Yeah, this is an interesting one as well. It's got density just under that of Earth, so I wonder why that is, because it's more massive than Earth, but it has a lower density, so I would assume that to be the other way around. That's probably a side effect of the equation we're using for defining radius. It's nice to see that we're not getting any extreme values. We've seen like 0.7 of Jupiter, 0.9, 1.3. There's been nothing that's been like ridiculous. A few gas giants here. Do we have any ridiculous ones? 0.6, 0.5, 0.69, 0.89. Yeah, so it means that the random weights are working, because it can have anything up to 13 Jupiters in terms of mass. It's capable of generating something that big. The fact that it isn't suggests that it's not weighted as such, which is what I wanted it to be. What's that around an M? That is that one. It's Y3. So that's like barely any mass. Yes, it's quite a big gas giant for something that's almost that size itself. Let's find a big star system. Now, it's lucky that this one's all gas giants, because if that was terrestrial planets, there'd be billions of them. Oh, this is interesting. So we've got a hot Jupiter, but it's really, really quite small. Ah, just took a note of that as well. So the density value that's being calculated is the same that as the one we entered manually, which means that the maths works because it's deriving the same value after going through all the various conversions. So that's promising. It's a tiny one again. A tiny one. Do any of these have life? Nope. 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 Nope, none of them have got life on them. Hang on, let's have a look at the temperature. So, yes, you class this one as a warm Jupiter, 597 C. So it's still hot, but not like thousands of C hot. Actually, let's sanity check that, shall we? So 870 Kelvin is coming up as a class 3. So on here, 870 would be between those. So yeah, there we go. So class 3. So that is right. That's as per the Zadarsky scale values, which I think I got from Wikipedia. Okay, so the planet mass that we were talking about should have been this. So 0.021, which is that. It must have been slightly over. Like literally just scraped over to be 0.02. Interesting. Okay, well, that worked, and the data values are there, so I think at just shy of 4 hours I shall call the stream there for tonight, and I shall go ahead and immediately put this out as a build. I guess the challenge with this build is have a look at the various different outputs for different types of planets and stars, and we need to get a feel for like how many planets there are per star system. Like, to me, looking at it at the moment, it feels like M-class stars break if the first object is a gas giant. Now that may or may not be realistic, but it's worth seeing kind of how that feels distribution wise. And also there's a 10% chance that gas giants will have life on them, so that's something to look out for as well. And I'm starting to lose my voice, as you can probably hear, so I think it's a good time to call it a night and get this build done. So thank you again everyone for watching. It's been lovely having you as always, and I shall catch you again on Sunday's stream at the usual time of 8 p.m. So thanks again, everyone, and bye for now.